Hi, Dr. Dan here. We're going to show today how to create movement in Unity using player input. And we're going to go over several different ways of making objects move around. So let's get started. First thing I'm going to do, I have a brand new project here. Let's save our scene as movement. And then we need some ground to move on. So I'm going to set up the ground as a cube. I'm going to scale it up to 40 by 40 for the X and Z axis. I'll rename it ground. And there we go, we have some ground. Alright, next up we're going to make something to move. So I like using spheres for this. We're going to set the Y-axis to 1 to just bring it up so we can see it. Let's make a few materials for the eyes. We'll make the eyes dark. Actually, we could make them nice and evil. Yeah, there we go. And the material for the body. This is just so we can see the player moving around and see which direction it's facing in. So its forward direction is this blue arrow right here. That's the direction we're going to move along if we add to the forward direction. I'm going to rename this sphere player. And then I'm going to duplicate it twice. Rename these eyes. I'm going to pull the eyes inside of the player and then scale them down to something like 0.2, and then let's pull the transforms out. So it looks like we have we're pulling them out along the z-axis, so let's make it an even 0.5. Let's zoom in, see what they look like here. Okay, that looks kind of good. And then I'll pull, oops, not both of them. I'll pull one over a little bit on the x-axis and the other over a little bit on the x-axis. And there we go. Let's give the eyes this red color. Ooh, it's going to look evil. And that body, let's make something that'll stand out. So see how that looks. Okay, cool. That's our player. So now we need to handle the movement. Let's take a look at what this looks like in the game scene. That looks okay to me. Maybe we can drag the camera up a little bit and rotate it down a little bit. So if you hit the Q, W, E, R, T keys, you get various ways of moving objects around in the world, and I just rotated it down along the x-axis there and moved the camera position up to 0.14. That all looks great. That's our game preview right there. So I'm going to save it, and now on the player we're going to add a move script. Make it a new C# script. We'll create and add. Alright. So on this move script, the first thing we're going to do is set up various ways that we might want to move using a enum. So we're going to do a public enum. We'll call it move type. I could type. And the way that you set up enums, so these are just custom types. They actually get interpreted as numbers by, in code, but we can call them whatever we want. So the first way we're going to move is by assigning vectors directly, so we can call that vector direct. The second way we're going to use is assigning rotation directly, so we can call that rotation direct. And we'll use the vector translate function to just translate from one vector to another. We'll use a Lerp function after that to show how to smoothly move between 2 points using linear interpolation. We'll then, instead of just messing with the vectors in update, in fixed update we'll mess with the physics of the player. So we could do a rigid body, and then we'll make that from the arrow keys, and we'll also do a rigid body movement using the mouse. Okay, so those are our move types. Now we need a way of knowing which move type we're currently in. So we'll make a public move type variable. We just created that variable type with the enum above, and we'll call that move type. Alright, so now if we save and switch back over to the editor, in player, you'll see we have this drop down where we have all the different types of moves that we've assigned. Right now they don't do anything except specify to the class that that's the move type we're currently interested in. Alright. The other thing we're going to need is a public float for speed. We'll set that to 10f initially, but we can adjust it in the editor because it's public. And we'll also need a public float for rotation speed when we start assigning rotations. Okay, so those are set. Now, let's get rid of this comment here. In update, we're going to have to set up a switch statement. So what we want to know, so switch is just going to ask us, hey, what move type are we currently in? And if we're in, so case, if we're in move type dot vector direct. So if we're in vector direct, we want to do some stuff and then break. Alright, so in vector direct, we're going to just grab our position, transform.position. So that's the position of the game object this is attached to, which is the player. And we're going to add our itself plus our speed, and we'll just multiply times input, and we'll get access, and we want the horizontal axis for x. So that's left and right, for our x values. So input.getAxis horizontal times the speed, and we'll add to that position like that. Oh, and one more thing that we'll add in just a second, which is time.delta time. So time.delta time is the time it takes between frames, and the reason we multiply it there is to get smooth movement rather than jagged movement. Okay, so it's not liking transform.position because it's not a variable. Can I modify the return value? Okay. So, interesting. So to get around that, in the beginning of update, we will have a vector3 called position, which we'll set equal to transform.position. So this is, the reason for this is that we have a read-only value here, and so what we need to do is assign that read-only value, so go get it, read it, assign it to something else, a vector3, and then after we're finished doing that, we'll then we can set the transform.position to position. So we can't directly modify the position, so we have to kind of go around that. All right. Now we want to do the same thing for our position.z value. So we'll plus equals speed times input x-axis, vertical times time dot delta time. Okay, cool. And that is all we have to do for the movement according to vector direct assign. So now if we hit play, and I'm going to mess with the arrow keys here, we get this nice movement, which is smooth because we modified it so that it goes between the frames. Now, this is nice for like strafing. You can tell you get full functionality. You might, however, want to be able to rotate in the direction you want to move and then move towards that direction. So that's the next kind of movement we'll tackle here. We have this rotation speed float already. So let's make another case in our switch statement. Move type dot rotation direct. We'll do some stuff and then break. Break is just going to break out of this switch loop here. So we want to break after each case, otherwise it'll run through all the cases, right? And it requires it. Alright, so since we're moving now in the direction of a rotation, we're going to need a new float, which we can call forward speed. And we'll set that equal to our value here. So the vertical forward backwards value. Okay. And then let's see, what else do we need to do? Let's have a rotation here. Another float that will store our rotation value in, and we'll make this equal to our rotation speed, and here we'll grab the horizontal. So instead of strafing with the horizontal x-axis, we're going to rotate the player, and the first thing we're going to do is just store a float value. Input.getAxis with vertical and horizontal returns a float between -1 and 1. So we're multiplying that float times delta, so 1 would be like moving to the right, -1 would be moving to the left, and then we're going to multiply times our rotation speed, which we set to 5. Okay, so when we adjust the rotation, we do so using quaternion objects. Quaternions are just complex objects in Unity that store rotation values in a way that instead of just storing them as vectors, which you can do with quaternion.euler, as we're about to in just a second, quaternion objects get around a problem of locking when we modify those rotation values. So we'll call this rot direct, and we'll set that equal to, so this will probably make more sense as far as a rotation. So if we do our quaternion Euler, we get to set the values as x, y, z values. And here, since we're only moving around the y-axis, right, we're rotating around the y-axis, so we're changing the way we face forward. Rotation is going to go right there, but because that's so we have x, y, z, right? So the y-axis will put our rotation value that we got, and then for the x and z axis, we'll use 0. So we'll ensure that we only rotate around the y-axis. All right, so that is how we're storing our rotation. How are we going to modify it? Well, we're going to use a transform.rotation because we're directly assigning the rotation here, and we'll do times equals our rotation direct value that we stored the rotation in. So Yeah, and then we still haven't done anything with position, so we need to do transform.position, and here we'll do plus equals forward speed, and we want to get the direction that is our transform forward, because that's what we're rotating around, the way the eyes are facing, right? So we're going to add our position to itself and then multiply by our forward speed. So let's save that, switch back to Unity, and now if I switch over to rotation direct down here in our move type enum, save and play and run the code. Now we see we have a very slow rotation. Okay, that's okay. That's why we made this adjustable in script. So if we set that to 10, we get a little faster. Let's set it to 100. That's a more reasonable rotation speed. So we rotate around, and then when we push forward, we move in that forward direction that the eyes are facing. Hello. Cool. All right. Next up, what is our next one? Translate. Okay. So now for translations. Oh, so we're breaking case move type. Translation. So the way that I want to translate is I want to have a point somewhere on the ground here, and when I click the mouse, when I left click the mouse, I want that point to be the new position that it moves to. So we're going to need to do a couple things. We're going to need to get the mouse position of the point as it translates to the ground. And then we're going to need to translate this vector position over to this vector position. Okay, so let's switch back to our move types. We're going to need a few more public variables here. So we're going to need a reference to the camera. And that's because the camera is what's tracking the mouse position in the game, and that's going to give us access to what the camera pointing at the world is pointing at, so the ground. We're going to need a layer mask. And that is going to be, the ground is going to have a layer mask that tracks the point that our mouse is pointing at when it points towards the ground from the camera. We'll need a vector3 goal and a quaternion for rotation. Those can be private. That's why I haven't put the public. Well, let's make them public. Why not? Why not look at them in the editor? We're only doing one class here, so I'm not too worried about public and private variables. All right, so we have the goal, the layer mask, something to store rotation in, and one more thing, we're going to need a public float for our stopping distance. So we'll need a distance to stop at before we get to the exact point. And the reason for that is that it's very hard to arrive exactly at the point when we're updating, 30 to 80 times a second, the vector positions of something. So what we'll get is like jittering around the point, unless we say, hey, if you've reached this distance to the point, go ahead and stop trying to get exactly to the point. All right. So now in start, we can set our cam equal to the main camera. So camera.main. We can set our goal to our current transform position to give it a default value, and our rotation to our current rotation at start. Again, we just want to get those default values. All right. So now our case translate, we're going to do some stuff and then break. And that stuff is, first we need to get the mouse position. So let's write a method called getMousePosition. And we can make this a private method or a public method, doesn't really matter. I'll make it a public method in case we decide to override this class and use it. And what we're going to do for this is we'll say if we get a click. So to do that we want input, and then the type of input we're looking for is get mouse button down, and the mouse button of interest is 0. That's the far left button. So if we get that, we're going to send a ray out. We're going to do that with this raycast hit first, and then we'll call our ray to be somewhere for our camera.main.screen to point ray input. Oh, we already have a reference to our camera. We only need one reference to the camera, so is that true? Do we only, I think that'll work, yeah. Input dot mouse position. Okay. Right. So ray equals cam. Screen point to ray returns a ray going from the camera through a screen point, and we'll get that from our mouse position. We can then say if our physics dot raycast, and then we have to feed in some parameters here: ray origin, ray direction times 1000 to give it the ability to actually hit the ground. And oh, sorry, physics.ray, we want ray, and then we have this output hit. Yeah, we want 1000. The thing we're looking for it to hit is our layer mask, which we'll assign in just a second. And then the final thing we want to do is query trigger interaction ignore. I'm going to ignore any interactions that get triggered. Alright, so if we get that, then we're going to do something. So if our raycast hits something, basically, if it hits the ground, then we want to set the goal, our goal, which remember is that public transform variable we made, equal to a new vector3, and for that vector3 we're going to use the x value of the ray where it hits. We're going to use our transform position of the y value, because we don't want to be moving around the y-axis. We want that to remain the same, and then hit .point.z. Alright, so we'll store that in goal, and then for rotation, we can store the rotation using the quaternion .look rotation function, and here we want our goal minus our current transform position. So whenever you have somewhere you want to get to, and you want a vector that's going to point from where you're at to where you want to get to, you want to put the thing that you want to get to minus the current position you're at. And that vector that gets returned will be a vector that points towards the thing you want to get to. A little vector math there. Alright, so that's our get mouse position. It's only going to fire if we click the mouse, the left click mouse button. So once we have the mouse position, now we can do some things with our transform. So once we do that, we're going to set our transform rotation to, and here we can use the quaternion lerp function, and we'll use transform rotation, the rotation we stored. So we're moving from our current transform rotation to the rotation we stored in and time.delta time times our rotation speed. So linear interpolation is the movement between 2 points according to a linear interpolation formula, and it happens in the time that you specify here. And so quaternion.lerp does that for you. All right, we need to store our direction. The vector 3 position. So we have the point that we want to get to. We need the direction to that point now. And then we'll say if our direction dot magnitude is greater than our stopping distance, and that's how we'll check to see if we're close and we need to stop, and if it is greater than our stopping distance, we want to move towards it until it isn't. So transform dot translate is the function we'll use here. Transform dot translate, and what are we translating? For translate, we're going to need to normalize the direction. So direction.normalize will return a vector with a magnitude of 1. And we'll multiply that times our speed, and then time.delta time to get a nice smooth transition that's modified by our speed. And this part's kind of important. The translation we want to make is in space.world. So local space refers to the space of your local object, and then space.world is going to say, hey, you know, put this local object and its position into this position in the world. All right. So cool, and that's all we need to do there. So let's switch back to Unity, switch down to translate, and hit play. And now, if I click, are we on translate? Yeah. Nothing happens. Okay. Okay, so perhaps that we do actually need to keep getting the camera in update. Alright, so where did we get mouse position? Down here. Alright, so instead of cam, which we initialize once, let's go ahead and grab the camera every time. So camera dot main dot screen to point right. Okay. And in that case, we don't actually need a reference to camera here or here. Alright, and let's check a couple other. Alright, so let's see if that fixed it first. No. Still not getting anything. Alright. I know what the problem is. Okay, so we don't have a layer yet. So in ground, we need to make a layer, and we can call that layer ground. Let's switch back to ground and tag it as ground. So now that that has a layer in player, we have this layer mask. We can just select ground as the layer. So let's save that, and now cool. So we're getting that rotation to face the direction we're moving in, and we're doing a linear interpolation on the rotation, and then a translate, which is another kind of interpolation, but just a function of the vector class, and we get movement from one point to another, and we can make the rotation speed faster if we want that turn to happen faster, or change the rotation values, but we're not going to worry about that right now. Alright, so so yeah, here we are using translation, and we're actually using a Lerp method, we can use that on the position as well. So we kind of took care of translate and Lerp together. I'll just mention that just as we used just as we use this quaternion Lerp, we could use a Lerp for instead of translate, we could do a Lerp there. Yeah, let's go ahead and do it. All right, so case move type. We'll use Lerp, and we'll get the mouse position again for this, and then we'll do the same thing for the rotation here. And now, oh yeah, let's add a break. So now we're going to say if our vector3 distance transform.position and goal. So remember, we get the goal set in our get mouse position. That's just the place that we're going for. If that's greater than stopping distance. So just as we used our direction.magnitude here to test for stopping distance, we can also use a vector3.distance and then just feed in two vectors and see if we're close enough to the stopping distance. We really get about the same result with those two methods for checking. So if we're greater than stopping distance, we're going to set our position to, and here we're going to use the same kind of Lerp function we use with quaternion, but we'll use a vector3.lerp. And we're going to lerp between our transform position and our goal, and we're going to do it in time.delta time. And we could multiply it by speed there as well if we wanted. Okay. So we'll see pretty much the same thing. We switch back to Unity, go to player and Lerp, and you'll see we're getting a much slower movement. That's because we're not multiplying times speed there. All right. Cool. So next up is rigid body. So to do that in Unity, let's go ahead and on player, let's add a rigid body. And we'll uncheck use gravity there. All right, and so this is happening in update. When we use rigid bodies, we want to use fixed update. So fixed update is when this it happens only once, and it's what we want to use for all physics functions like rigid bodies. We need a reference to that rigid body, so public, actually this can just be rigid body RB. And what else do we need? We need to then yeah, we need to get that component. So we're going to get our own rigid body there, component, and get a reference to it. And then in fixed update, we'll make another switch statement. So both of these updates will run, and we'll switch again on move type. And open that up. All right, so we have two cases. We have case move type dot rigid body arrows, and we have case move type dot rigid body mouse. All right, for rigid body arrows, we want to set our goal to our transform forward first, because we're going to move in the forward direction. We'll do a float translation and make that equal to input dot get axis vertical times speed, so that's our up-down speed arrows, and then a float, which we can call rotation. We'll make that equal to input.getAccess horizontal, and we'll multiply that times our rotation speed. Now, for our translation, let's multiply that right here times time.delta time and it, itself. Translation times equals, what's wrong here? Oh, translation. There we go. And then we'll have a new quaternion, which we can call turn, and set that equal to our quaternion angles, quaternion Euler angles, which will be, again, 0f. So same kind of thing we did above with, rotation, and we'll actually want to put rotation here times equals time.delta time as well, and then 0f. So we're rotating around the y-axis again, and now all we have to do, since we're using the arrows, is rigid body has a move position, which we can set to the current rigid body position plus our transform forward times our translation. So translation is just translating the -1 to 1 factor we get from get access vertical into a speed, so into the amount that we're going to move forward or backwards. Move rotation is another method of rigid body, and for that we're just going to get our turn, which is our Euler y rotation translation of the of what we're getting from our horizontal arrow keys, and rb.rotation is what we're going to multiply by, and that's it for that. So if we switch into Unity and we change our move type to rigid body arrows and hit play, now when we rotate very slowly, you'll see that we're moving, and we're moving forward in the direction of the rotation. So where's our rotation speed? It's at 5. If we set that to something more reasonable like 100, we'll get a nice smooth rotation there. Alright, so I'm going to go ahead and set rotation speed to 100 here when it's not playing, so it remembers that. Alright, so the final thing we're going to do is use the mouse position, and we're going to use our rigid body to push around towards that mouse position in our move types. So rigid body mouse, the first thing we're going to do is you gotta get our mouse position. Again, we'll send a ray cast out from our mouse, from the screen to the point at which our mouse is pointing at on the ground. And after we do that, we can have a quaternion. We'll want to lerp towards this rotation. So we'll set that to quaternion.lerp. So putting everything together, just as we use lerp in the translate, we're going to use it here, and we'll use transform.rotation. The rotation we're lerping from, the rotation we're lerping to, which is rotation, which we set in get mouse position, time.delta time, and times, we might want a speed for lerp rotation. Rotation speed. Let's add that up here. So it's going to be a little different. And for a default value for that, maybe like 2. We don't want to multiply it by too much because we're doing a linear interpolation, so that multiplies times itself. Alright, so we were down here. Alright, lerp rotation speed. that takes care of our of getting our rotation. Now we need to actually set our rotation. So rb.move rotation to our Lerp rotation. Okay. Finally, we need to check again if our distance is appropriate. If we're transform.position, the distance between that and the goal is greater than whatever we set our stopping distance to. Then we want to go ahead and move, but we're going to move with the lerp function again. So we'll set a lerp target, and we'll make that a vector3, which is our transform.position vector3 lerp, sorry, which we want to lerp from our transform.position to our goal, and we'll do it in time.delta time times the speed. And then we will just move our position to that lerp target. And we want to do so by adding the transform forward. Because remember, we're just moving forward in the forward direction. Rotation's taking care of what direction it is we're moving towards. And we'll multiply that times speed and times time dot delta time. Alright, and that is it. And then we break. So final type of movement here, we want to set that to rigid body mouse. So we have this rotation speed and lerp rotation speed. Cool. Alright, let's save it. Now as I click on things, we're getting very fast jumps. We are actually lerping. You see the rotation lerp is not really synced up with that. That's because rigid body move moves a little faster than directly setting the transform. So if we set that down, and we can even turn this up to like 200, so that happens a bit faster, not 1200, 200. We get this nice rotation towards a point. There we go. Cool. All right, that is 1, 2, 3, 4, 5, 6 types of movements, and how to implement them all. This is all just player movement. So things like setting an AI to move between points on the screen or to move towards the player. The only thing you're really going to change with these movement is the goal, right? So just as we have a goal, which is our transform forward, that goal could be an array of of game objects, and we could be like going through each game object G and goals, and then saying like goal equals goal dot position or transform G dot transform or position. There we go. And then doing something with those with an AI, we could then be moving towards that position and rotating towards it using any of these functions. So this basic setup for moving in different ways at different rates with like different types of linear interpolation will work for AI as well. And it's I should also mention that get access, all we really need for this is some kind of value between -1 and 1, and we could set those as we get input from the mouse, from a controller, from VR. Doesn't really matter as long as we get a value between -1 and 1. All this will still work. And if we don't get a value between -1 and 1, we can normalize it and make it a value like that. That is all. that was 6 types of movement in 45 minutes. I hope you enjoyed that tutorial on player movement in Unity. Thank you for watching.